Welcome back to part 1, Foundation. And as I told you, I'm going to start this lecture by discussing the fancy things like the Jarzynski equality and the fluctuation theorem. But since we have to discuss what we get from mechanics and equilibrium statistical mechanics, I have to give a brief discussion of classical Hamiltonian mechanics. That's what I'm going to do in this video. So probably most of you know about this. So then you can just check our notation. So we consider a system of n classical particles in d dimension. D is basically 3, but it can be 1, 2, 3, or 5, whatever. And I call these particles like by using number j equal 1 dot n, and by vector rj, I denote the position of the jth particle, and by vector pj, I denote the momentum of the jth particle. It's in Rd, and in this case, Rj lives in lambda, which is a finite subset of Rd. You can imagine that this lambda is a finite box in 3 dimensions, okay? And then by uppercase x, I denote the collection of all these positions and momenta. And this x is called the phase space point. Okay, it describes the microscopic state of this n particle system. And x lives in this set gamma, uppercase gamma, which is precisely this. And this huge space, it's a 6D dimensional space if t equals 3, and this space is called the phase space. Okay, now a general time-dependent Hamiltonian h of tx is a function of time and the phase space point. And this is a general form where you have time-dependent vector potential, scalar potential, and time-dependent external force and interaction between particles. Okay, but you don't have to worry about this precise form. Okay, then now this, as I said, T denotes our time, and now we consider a trajectory. That is the time-dependent phase space point. So it's a collection of time-dependent r positions and momenta. And this is determined by the equation of motion, and in this case, it's called Hamilton's equation. And these are the Hamilton's equations, and this r dot is determined by this partial derivative of Hamiltonian, and p dot is determined by this. So this is essentially the Newton's equation. Okay, and as I said here, of course, this is a general n-particle system. It's basically impossible to solve this kind of coupled equation of motions. But we can formally write this down, and we can formally discuss its solutions. And this T of T is a very important object that we call time evolution map. It's a map from this phase space to phase self, and it describes the time evolution from 0 to t, determined by a general Hamiltonian h of tx. And what it does, it simply maps any initial state to the final state. By initial state, I mean the state at time 0, and by final state, I mean the state at time t. Okay, so you feed any initial state, then it outputs final state, or the corresponding final state. So we assume that of course, such map of course exists, and we don't know the precise form, but we can use it. And we assume that this TT is a 1-to-1 map from gamma to gamma, and this is always the case for usual Hamiltonian, so we can safely assume this. Okay, these are just formal notation, and here's one important discussion about time reversal symmetry. So this is an arbitrary phase space point, and then we define its time reversal x star. This has nothing to do with complex conjugate. This is our definition. By x of x star, I denote almost the same thing, but with all momenta flipped. Okay, so the positions are the same, and as for momenta, we just put minus sign in front. Okay, then we consider any time-independent Hamiltonian, which doesn't depend on t, and with time reversal symmetry in this sense. So this says that Hamiltonian does not change if you flip all the momenta. And of course, there are many Hamiltonians which are not time reversal invariant. So if you look at this term, and if you have vector potential, and if you change p to minus p, then of course the form changes. So in this case, the Hamiltonian is not time reversal symmetry. So for example, this kind of simple Hamiltonian without magnetic field is time reversal invariant. Okay, if you put minus sign here, it doesn't matter. You have square here. Okay, so this is an example. still contains many physical systems. And I denote by TT the corresponding time evolution map. Then by time reversal symmetry, we say that there is symmetry like this. And this is a very complicated equation, but it says very simple thing. So you'd better look at this picture here. So you start from here, this position, and this is a velocity. And this particle goes like this. At this position, you just, okay, so this is the initial state. This is the state after time tau. Tau is some positive number. And then at this moment, you flip the velocity of this particle, and you don't change the position at all. And then you let it go. But you know what happens? I mean, it came like this, but you switch the velocities, and so it simply goes back. And after exactly the time tau, it goes back to the original position. So it comes to the same position, but you know, the velocity must be the opposite from the beginning. Okay, so this is it. So probably it's easier to see this. So this equation 6 describes this situation. You start from x, and you revolve the state by time tau, so you get this. And then this at time tau, you switch all the velocities, all the momentum like this, all the momentum like this. So this is a momentum flipped state. And then you let it evolve by time tau, this, and then you end up with state x star. Okay, good. So, and in order to make this simpler, it's not simple, but if you take star of everything, you get this thing. Okay, so this is the time reversal symmetry. Good. And proof, of course. Yeah, and this looks just obvious, and I think you don't need a proof. But this is a lecture, so I want to be complete. So this is a proof, but you know, it's just simple. So suppose that this xt is a solution of Hamilton's equation like this, and then I just consider time reverse trajectory like this. It's the same thing. It's basically the same thing, but it's written as a function of s, and s is this is a reversed time. Okay, t, our original time goes from 0 to tau like this, and then s, this new time, goes like this. So this s is basically defined by the equation that this is equal to t, right? So if s goes from 0 to tau, and then inside here, this goes from tau to 0. Okay. Anyway, so let's write this x tilde like this, and of course it's written like this. And then you examine what equation of motion do these r tilde and p tilde obey. And it's quite easy. So if you just compute the time derivative, and then by using this relation, you can relate it by use like this. And this r satisfies this Hamilton equation. And then you rewrite this by using x tilde like this. It's basically x star, but x tilde like this, and use this invariance. And okay, as for p, yeah, the same thing. You use this relation to get this, and p obeys this, so you get this, you write this. And anyway, you look at this left-hand side and the right-hand side, okay, and compare. Then you find that this x tilde s obeys exactly the same Hamilton equation determined by exactly the same Hamiltonian h. Okay, and this, if you think a little bit, justifies this picture and justify these relations, this relation. Okay, good. So that was a proof, and let's continue. And one more thing, we have to discuss something called Liouville's theorem. Okay, and what does it say? Well, it applies to any Hamiltonian mechanics, any Hamilton's equation. And it said that the time evolution map T of T for any Hamilton mechanics preserves the phase space volume. What does it mean? Well, so this is a simple case with d equal 1. So the phase space is just d equal 1 and n equal 1. Okay, one particle in one dimension. And in this case, the phase space is two-dimensional space, position and momentum. And here you consider it need not to be a small, but you consider a phase space, a region in this phase space. And suppose that you trace the time evolution of each point in this region. So here, this corner goes here, this corner goes here, this inside point goes here and here. And then this T of T defines a new region, right? And the Liouville theorem says that if you measure the volume, in this case area, of this new region, it's exactly the same, P. Okay. Well, I will prove this, but if you don't know this, probably it's better to look at simple example. This is quite illuminating, I think. And so consider very simple equation of motion for one particle in one dimension, n equal 1, d equal 1. So this is r dot equal m p over m. This is simply says r dot equals the velocity, and this is the equation of motion. So this is a force. So in this case, the particle feels a force which is position dependent. If it is at position r, it feels the force Fr. And also here's this resistance. Okay, I assume that there is a resistive force which is proportional to P, and this is a proportionality constant. Okay, and of course, probably you know that you never encounter this kind of resistance in a Hamiltonian mechanics. Okay. In Hamilton's equations, you never get this, right? So this should be, gamma should be 0 if you're considering Hamilton's equations. But it will be useful to consider this. Okay, you will see. Okay, so now I consider time evolution by very small amount of time, delta t, and only consider first everything in first order in delta t. Okay, and here's some notation. I consider position r0. So if 0 denotes the force the particle feels at position r0, and I also consider position r0 plus delta r. This is small thing, and then I consider this delta f, the difference between this and this. Okay, and now I examine how this region in this two-dimensional phase space evolves after time delta t. Okay, so let's examine. So you look at this corner, left bottom corner of 0, P0, and examine how does it evolve. Well, this is very simple. R0, the position moves by delta t times the velocity. Okay, and this is P0, so P0 changes a little bit. P0 changes plus delta t times, this is a force acting on the particle. And in this case, the force is this external force, if 0, if not, and this resistance minus gamma P0. Okay, and let's call this R0 prime and P0 prime. Okay, there are 4 points, so let's consider the second one. And now, if you start from R0 plus delta R P0, so this right bottom corner, and then it evolves to this. This is exactly this. This is quite simple. And P note, this momentum evolves to this. This is a force acting in this case. And now force is a little bit different, slightly different, F0 plus delta F minus this resistance here. And now, so you can write this as R0 prime, B0 prime plus this thing. And let's call this one a vector. And now the rest are exactly essentially the same. If you start from here, you get this. So let's call this B vector. If you start from this, and then in this simple calculation, you simply get A plus B. Okay, so let's summarize the situation. This is our equation of motion, and then if you consider this small phase space region, and then this is mapped to this. And now let's look at the area. So in this case, area is very simple. It's delta r times delta p. In this case, if you want to compute the area, the best way is to consider the vector product of these two vectors and take the z component. That's kind of simple mathematics, which I hope you learned in freshman course. And anyway, if you compute this vector product, you get this. And of course, this is higher order than you can just ignore. We are interested in the first order in delta t. And now, if you compare this and this, it has this common factor and this prefactor. And this prefactor is strictly less than 1 if gamma is positive, if you have resistance. And so this means that this area is the area preserves if and only if this gamma, the resistance, is 0. Okay, and we know that gamma equals 0 means that this equation of motion, these equations of motion, follow from a Hamiltonian. Okay, if gamma is non-zero, you don't have any Hamiltonian equation. Okay, so this tells you that this is just an example, but this tells you that if you have a Hamilton's equation and the corresponding time evolution map, then it's very likely that the phase space volume is preserved. Okay, so that is Liouville's theorem. And this is how we are going to use Liouville's theorem in our lecture. And okay, again, this TT, the Liouville theorem says that the time evolution map TT determined from any Hamilton's equation preserves the phase space volume like this. Now, we can use this in the following way. This is the general phase space point, and we often consider integration by phase space point. And the natural integration measure, the Lebesgue measure, is this. It's simply dx. If I rewrite dx, it's simply the product of all this. This means that dx, dy, dz. Anyway, this is a standard integration measure. Okay, and now we fix tau, a positive tau, and define x prime like this. Well, of course, it's a time evolution of x. But anyway, you can look this as a change, one way of changing the variable. So x is a variable for phase space. And then for fixed tau, you can define new variable characterizing the phase space by x prime by this way. Okay. And so now you can express the phase space point by using this new coordinate x prime, and you can also consider the corresponding integration measure dx prime. And what we want to say is that the Liouville theorems guarantee that this dx and this dx prime are the same. Okay, of course, you want to have a Jacobian here, or you want to have a Jacobian if you're an American. You want to have, anyway, something here. And this tells you that Jacobian happened to be 1. And actually, you can, if you sit down and think, you can easily convince yourself that this volume preserving precisely means that the Jacobian is 1. Okay, actually, that is the meaning of Jacobian. Okay, so this is something. This is the only thing you have to have in your mind to understand, say, the Jarzynski equality and the fluctuation theorem and the detail balance condition and so on. So this is very important. And actually, you can stop here. Okay. In order to understand the Jarzynski equality, you can stop here and go to the next video. But since this is a lecture, I want to be complete. So from now on, I'm going to talk about the proof of this Liouville theorem. And to prove this, I'm going to go through something called Liouville's equations. And this is actually not a direct proof, but this is a very standard proof, and it's also illuminating. And actually, it will be also. Liouville's equation will be useful in our part 5. It's still some time to go there, but this will be useful in our part 5. So I think I'm going to go through this proof. But anyway, you can just skip and go to the next video. Okay. Okay. Also, thank you for staying. So let's continue. So now, for some reason, I want to consider the notion of probability density. Okay. Probability density P0x, P0x, I think you know, it's a function on phase space, and it's non-negative. And if you integrate, it gives you 1. And its meaning is this. If you take any subset S of gamma, and if you integrate this P0 over S, then this gives you the probability to find X in S. Okay, that is the meaning of probability density. Okay, so this P0x is not itself is not a probability. If you multiply this by phase space volume, then you get the corresponding probability. Okay. Now, I assume that initial state x0 is distributed for some reason according to this probability density P nodes X, P0X. Okay, so it's something like this. X0 is distributed over phase space like this. So somewhere you have higher probability, here you have zero probability, here you have small probability, and so on. And then you let this evolve by some amount of time t. So after some time t, this goes here, this goes here, this goes here. So you started from this dot pattern of dots, and you trace each dot. And then after here at this time, you have a new pattern of dots. And you can think about the density. You can consider the density of here, and the density or probability density here is denoted like PTX. It's a probability density, the probability distribution of x of t for a given fixed t. And in equation, it's determined like this. Okay, so what is this? Well, this says that y is initial state. Initial state y is distributed according to this P0y. And then if you evolve this y by t, and then this tty must be equal to x. So here's delta function. Okay, so this is a definition of this notion. Okay. And then this is one form of Liouville's theorem. Usually Liouville's theorem says that you take any Hamiltonian and corresponding mechanics, and this is trajectory, time evolution map, and this probability distribution. Then Liouville's theorem says that for any solution xt, this is true. This is an easy equation, but it's not easy to understand. So this says that the density around you is invariant. So suppose that you are here, and it's kind of dense. And so the density around you is kind of dense. And if you go here, and then if you look at your neighbors and you examine your density, again, it's the same. It's again high. And if you start from here, the density is very small. And if you go here, and then you find the density around you is still the same. It's very low. So the density is always preserved. And this is not an easy trivial equation. This looks like a trivial equation, but you need a proof. Okay, this holds only for Hamilton mechanics. Okay, so this is not a trivial thing. And of course, you can write this exactly in this way. And before proving, so we're going to prove this. But before proving this, I want to tell you that this implies the volume preservation that we discussed. So this is the Liouville's theorem, okay? And then this says that, okay, if you start from any phase space region and if you evolve it, then the volume is the, no. Your density is the same. I'm sorry. So I want to say that this implies the volume preservation. Okay, so you take arbitrary region R0, R0 in phase space, and I denote by V the volume, 60-dimensional volume of this region. Okay, and now since P0 was arbitrary, I define this probability density. Okay, it's simply 1 over V. It's constant when X is within R0, and it's 0 outside. Okay. And if you integrate, you get 1. So this is a good probability density. Okay, now we use this Liouville theorem in this one. And this simply says that this PTX is also either 1 over V or 0. It's constant. And it's 1 over V if X is inside TTR0 because of this. And it's 0 if it is outside TTR0. And from this, you observe the volume preservation easily. Consider this integration. Okay. Since this PTX is given by this is simply given by 1 over V times volume of this new region TTR0. Okay. But since this is a probability distribution, this integrates to be 1. So this is 1. This means that this volume must be V. Okay. So the volume is preserved. Good. So so now you're convinced that this is what we want to prove, okay? Or this is what we want to prove. So now I will prove this. I will prove this by using something called Liouville's equation. Okay. Now here's the proof. It's just easy and formal. And now I start from new notation. Okay. To begin with, this X was an object which consists of all these position and momentum. And this is notationally very much complicated. So let's introduce new, simpler notation. I simply call the elements of this components of X like as lowercase x. And this x1 to the xd, and this d is to the n. So actually, half of these are positions, and half of these are momenta. Okay, but anyway, this is simpler notation. And then I rewrite Hamilton's equation in this form. And this is quite easy. This x dot equal v, very familiar notation. But what is this v? If you recall what this Hamilton's equation, it's a bit complicated quantity. Vj for this case, where xj is position, and then this is given by the partial differentiation of Hamilton h with respect to momentum. So in this case, you add 2 of d over 2. And so this gives you the corresponding momentum. And when j is in the latter half, then xj denotes momenta. And in this case, xj minus d over 2 gives you the corresponding position. Okay, so this precisely recovers. So please look at this. This precisely recovers the Hamilton's equation. It's a bit complicated, but that's a point. And I just say that this is also precisely written by using this tt. This is written like this. Good. This is basically the notation. And I first argued that this pt of x satisfies a very familiar equation called the continuity equation. You have seen this in many places like electromagnetism, fluid mechanics, even in quantum mechanics. So whenever you have a preserved quantity, you have this continuity equation. Okay, and in this case, the probability is conserved, and you must have this. So this is basically the J's component of the probability current, and you take the divergence minus, and then this is equal to the time derivative. Okay, so this is so trivial, and you don't need a proof. Or you can even declare that this one is the definition of PTX. In our case, we defined it by using this delta function. But if you don't like this, you can use this as a definition. But anyway, since we use this as our definition, we're going to prove this. And of course, it's trivial, and it's simply the matter of notation. Okay, so now I want to prove this. So I just use this definition and take differentiate by time. I didn't do anything here. And now here you see t is here, and there are d objects, and this is a product of d things which contain t. So you usually use usual rule and differentiate these things one by one. So you differentiated this with j. So this one was differentiated, and these guys were not differentiated. Okay, so this is a product of d minus 1 things, k equal not j. Okay, and if you differentiate this with j by t, what you get is simply, if you differentiate this, you get this minus v, and you have to, by differentiating this, you get delta prime. This is the differentiation of delta function. But now this prime, if you look at this, you have xj inside here. So you can rewrite this like this. You can differentiate this delta function by this. But now you don't have any xj. This is the only place you have xj. So you can pull this xj out here. And then this becomes simply delta function, and it becomes like this, and you have v. Okay. This is complicated, but everything is very simple. And now if you look at this carefully, you have this y integral here, but here you have delta function p0y. So you can perform this y integration to get this ptx. This is basically this definition here. And you have this extra v here, and now you look, you get precisely this. Okay, so that was the proof of the continuity equation. Good. Now I can prove, so this is the end of this video. This is a final slide. Now I can prove Liouville's theorem by using Liouville's equation. here. Okay. Now this is the continuity equation. And now here, this is a product of two things, and I want to differentiate with this xj. So let's do this. So now this consists of two terms. If you differentiate this one, you get this. If you differentiate this one, you get this. Okay. Now I argue that this summation is vanishing. It's zero. Why? Well, this here we use the fact that we are dealing with a Hamilton mechanics. Okay. Now I'm summing over all j this, and recall that this xj was sometimes position and sometimes momentum. Okay. And so I decompose this summation into the first half and the second half. In this case, xj is momentum. And now Vj is given by, no. In this case, xj is a position. And xj plus d over 2, this one is the corresponding momentum. And Vj is precisely given by this. Okay? And you differentiate this by xj. Now, if you look at this here, now j in the latter half, xj is a momentum, is a component of momentum. And this Vj is given by this, right? And then you differentiate by this. Now, if you look at, and you have minus because of Hamilton's equation, and if you look at this very carefully, well, you can check this when d equals 2. That's very easy. You see that you exactly get the same thing, and it's 0. Okay? So this works only when you have Hamilton's equation. Okay. And so what did we get? Okay. So we have seen that this part is vanishing. And so this is equal to this. So this leads to this very important equation called Liouville's equation. This Liouville's equation tells you how this probability density evolve in time when the corresponding x obeys Hamilton's equations. Okay, so this is very important equation called Liouville's equation. And we are almost done. What's our goal? Our goal was to show that this is 0. But this is very, very easy now. So you are interested in this, and this consists of two parts. If you differentiate this, you get this. And if you differentiate this, you get this. And you compare, there's no, this is no mistake, this is plus. And if you compare this with this, then you get from this Liouville's equation, you find that it's 0. So we are done, okay? We have seen that this is equals to 0. What was our goal? Our goal was to show that this equality is correct, and we have shown that this is time independent. And then, of course, you have this. Okay, so we are done, but let me just rewrite this Liouville's equation in a more familiar form, because this x and v were very formal notations. This x sometimes represented position, sometimes momentum. So let's consider the very simple case of this Hamiltonian, and no magnetic field case. Consider this very standard simple Hamiltonian, and rewrite this Liouville's equation explicitly using r and p. And then you get this form. Okay, this differential time derivative of ptx is given by this, and there are two terms. This term simply represents the fact that this p over m is the velocity, and r changes according to the velocity. And this term basically corresponds to Newton's equation. This is a force acting on the particle, and this simply shows you that the momentum changes according to the force. Okay, so as I said, this is a basic equation that tells you how this probability density evolve in time when these r and p evolve according to Hamilton's equation or Newton's equation determined by this Hamiltonian. Okay, so I'm done. So this is the end of this classical mechanical part. And in the next video, I'm going to discuss the Jarzynski equality.